Okay, so now that we've explained the concept of refraction of light following Snell's law, we stated that one of Snell's law said that the ratio of sine of angle of incidence to the ratio of sine of angle of refraction is a constant for a given pair of medium. That constant is the refractive index of the material. We're going to use our glass block. So we have the glass block here, rectangular glass block. So we're going to see how we can determine the refractive index of this block following Snell's law. Remember, the first of Snell's law states that the incident ray, the refracted ray, and the normal at the point of incidence, the three of them, they lie on the same plane. The point of incidence is this point where this incident ray, this refracted ray, and this normal, where the three of them meet, all right, is called the point of incidence. That the three ray, they lie on the same plane. Of course, the plane is this plane AB. So you can see three of them meeting on that plane, right? So we're going to verify this law. Sine I over sine R is equal to the refractive index of the given pair of medium. So I believe that we are ready to do the experiment. Is that okay? Good. Now we are going to demonstrate Snell's law of refraction, one of them, okay? That one that states that the ratio of the sine of angle of
incidence
to the ratio of the sine of angle of
refraction
is a constant for a given pair of medium. Question: what are the mediums we are going to use for this experiment? Good. I will show you some apparatus that we have here. This, a rectangular glass block. Please, can you show our friends at home the pins we are going to use to represent the rays of light here? You just show them 1, 2, good. You can see the pins we would use, all right? Then we have our tracing paper, okay? We'll do our traces and this. We'll do our traces and this. Remember, all we are interested in is to show the angle of incidence with the incident ray, angle of refraction with the refracted ray. With these angles, we can now calculate the refractive index of this glass block. Are you ready for this?
Yes.
So let us carry our friend along at home as we do this, so that when they go back to school, if your examiner asks you question on how to carry out experiments using rectangular glass block, of course this is called optics. Is that okay? It's called optics. You won't have any challenge in doing that. Now we would go behind to start running the experiment for you, so that you can see what we are doing. In the meantime, you won't see our face, but you'll be seeing our hands, all right? Going along what we are expected to do. As a summary, this is the procedure of what we're about to do. We will trace the outline of this. We're going to place it on this tracing paper. Then, with pencil, we would bring out the outline. It's a rectangular block. And then, we will draw what we call the normal. According to Snell's law, one of his laws states that the incident ray, the refracted ray, and the normal at the point of incidence, all the three rays lie on the same plane. That is what we're going to do, drawing those rays. The incident ray will fall on this glass from air. Our surrounding is what? Air. And then, once it is incidented on this block, we expect that this block will cause what? Refraction. So those two rays we are very interested in it. Please follow us as we demonstrate Snell's law quickly. Let's do this.
Viewers at home, we are going to use an incident angle of 20 degrees. But first, we need to draw the outline of the block.
That's correct. Now that we've drawn the outline of the block, we are going to draw what we call the normal. The normal is simply a perpendicular line drawn to one of the outline at 90 degrees. Now I'm going to show you the outline that we've drawn. Can you take a look? That's the outline of the rectangular glass block. So with this outline, we'll draw a normal at a point. We're going to pick a point just a bit close to the center, but not exactly center. We're going to use this. So this is going to be our point of incidence. There we'll draw the normal. So you watch as I draw the normal. We need protractor for these. We need protractor. So look at this part of the protractor. Look at this. I will place it at the point of incidence. This point where 90 degrees and the 0 to 180 degrees line met. All right. I'm going to place this point at our point of incidence. And then I will draw 90 degrees. I will ensure that the 0 to 180 degree line is lying on this plane which I will call AB. So this is what we have here. Look at my 90 degrees here. This is my 90 degrees. So the line of 90, I'll make a dot there. All right. Take off my protractor. I will need to use ruler now to join this point of incidence. This 90 degrees line rather. Okay, the 90 degrees line, I'm going to join it to this point of incidence that I'm using. Good. So you can see how wonderful the 90 degrees line is. Like you heard, initially we're going to incident a ray of light at 20 degrees to this normal. How do we do that? I will take back my protractor, and then with the protractor, I'll place it exactly the way I placed and obtained the 90 degrees. Okay, so let us see how it goes. I'll place it back exactly the way I got that 90 degrees. No mistake, take note. And then I will measure 20 degrees away from 90 degrees. 20 degrees away from 90 degrees will take us 70 going to the left. From 90 to 80 is 10. From 80 to 70 is 20. So there I would put a point. So I have a dot which I will now join to the point of to the point of incidence. Let's do this and see. Look at the point. That is the 20 degrees down to this point of incidence on this plane. I will join these two lines, and that gives me my incident ray of 20 degrees. So this is 20 degrees. I'm going to write I equal to 20 degrees. This is my incident ray. So this is much of the first thing we are going to do. The next is to place our glass block back, and then we will place two pins on the incident ray and find the image on this side. So follow along as we do that. Okay, now we are set to get the refracted ray, which will help us to get a refracted angle for us to be able to calculate the refractive index of this glass block. Now, at this point, we need to replace the rectangular glass block on the outline that we drew. So you're going to replace the rectangular block for our viewers so they can see it. Go ahead. So you see that we'd have to ensure that the rectangular block is placed as much as possible perfectly on the outline that we drew using it. Good. Now that we've placed it, the next thing is to place our tracing pins, all right, on the incident ray. So let me put the first tracing pin. You can see that. Let me put the first tracing pin. Don't mind me that I'm fighting with the tracing pin. Okay, so we go. All right, trying to I've fixed the first one. Then we need 2 tracing pins. Take note, you must fix 2 of the tracing pins. And you need to give a distance between the both of them. So these 2 tracing pins that I fixed will serve as our incident ray pins, okay? Those are the objects. You can see that. Our aim now is to get the emergent ray here, the point where the ray will come out. The ray that will come out here is called the emergent ray. Once we're able to get the emergent ray, our problem is solved. We can now join the point where the emergent ray came out. We can now join that point to our point of incidence. But how do we get this emergent ray? Now, you'll listen to this, very important, because this is where this experiment becomes, should I say tough? Of course, nothing is tough. The principle is very simple. So you now watch what it's going to do. We are going to look through this face. We would squat and look through this face of the glass block. As we are looking through the face, we will be seeing the image of these pins. When we look through here, we'll be seeing the image of these pins. But the principle is we are to stand or squat rather and look through this face in order to see the image of only this pin. The image of this pin is expected to block the image of this second pin. All right, so that is what we are now going to demonstrate. I will turn the camera to help you to see the next thing that's going to happen, so you can see how he squatted, and then we are going to trace the image of these pins here. I hope you're seeing that. But before you do that, you must be able to place yourself on a straight line to the image you are seeing. Let's assume you are seeing the image in this direction and you are standing here. You'll be doing something wrong. Or you are standing here or squatting here, you'll be doing something wrong. The direction you are seeing the image is the direction you are expected to squat, because you're trying to block something. So you now watch. Once again, I'm going to place this so that you would be able to see the image with us. So please, viewers at home, take a look. Can you see the image of the pins? Good. If you look through this face, you'll be seeing the 2 images. Look at one of the image, then look at another one. I take that again. This is one of the image, then this is another one. The position I am squatting to point to these 2 images is very wrong. The principle is you are not allowed to see this image, the image of the second pin. You should squat at a position where you'll be seeing only this image. That is the rule, because this pin is expected to block this one, which means we have to shift to this direction. Look at this direction where the ruler is, because if you follow that direction, you will notice by moving your eyes, closing one of your eyes and looking through this face, you'll be seeing only one of the pins. So watch as we demonstrate it. Please, can you place the pin at the position where it will block?
On this side I'm staying. I can only see one of the pin at this angle.
Good.
So one pin should go here.
Then make sure that you are blocking the image of the first pin. Okay? Good. You've been able to place one pin. Of course, you know it's still left with one. Is that not so?
Yes.
At this point, he has placed this pin. And according to him, this pin blocked the image of what he saw through the glass block. The next thing he's going to do is to find a way to block this pin now. The whole idea is that the 4 pins, which are the images of the pins through this rectangular block, and the pin that he used in blocking them, together with the next pin he's going to put here, all of them should be on a straight line. So watch as he blocks the emergent pin that he just placed.
So I put the pin here to block the pin I just put.
Now stay in that position. They need to see the angle or the point where you are staying. Can you people see that he needed to move, and perhaps he moved to that end, all right, to the other end, in order to be able to block the image of the pins that he saw through the glass block. Now I will position the camera so that you view yourself and see that yes, he actually blocked the pin. Please, viewers at home, our dear friends, can you watch from this angle? Did you notice that you are seeing only one of the pin, which is this? All right, so we've done a very great job. The position I place the camera now, you are only seeing this pin. The rest three have been blocked. Remember, you look through the foot. If you're looking through the foot, you notice that this is the only pin you are seeing. This is the only pin you are seeing. Let me adjust the camera and you will see what's going to happen. Do you notice that you're now seeing two pins? You are seeing this and you are seeing this. If I move again, you will notice that the images of the pin through the glass block, this face, you can now see them. In fact, you are seeing 4 pins, 2 images and 2 objects. This position is wrong. If you're standing here and you are viewing, you can never block the pin. Remember the rule. Position yourself such that you yourself that is trying to block the image of the pins looking through this face, you are on a straight line with the image you are seeing through the glass block, so that you are seeing only this image, the image of this pin. The second one should be blocked. So I am moving again for the last time to the direction that this needed to be, which is what we did wonderfully. This is great. Well, let's get a knuckle before our viewers at home that we've done something great. All right, now that we've shown you how you block the image of the incident ray pins, all right, how you block this, the image of these pins using these 2 emergent ray pin. What do we now do next? Can you please speak to our viewers?
Next, we remove the glass block and the pins. So we can use the ruler and the pencil to join these 2 points to the glass block. Make sure the line is straight to form your emergence ray. And after that, finally, you now join this point where the emergence ray met the glass box to this point of incidence to form your refracted ray, which looks something like this. So this will be your refracted ray. This will be your emergence ray.
That's great.
This is your incidence ray.
That's great. So you see this, right? It's a simple one. It's a simple one. We've gotten the incident ray, the refracted ray. Now this angle is what we call the refracted angle. So let me put arrow degree there, okay? Arrow degree. We are going to measure the refracted angle now. We are going to measure the refracted angle. So watch as we measure the refracted angle. Watch as we measure the refracted angle. To measure the refracted angle, I'm going to turn this protractor this way. Remember, this refracted angle is formed by this normal and this refracted ray. So, this is the point from which the angle was formed. This point, which is the point of incidence, will be at this point where 90 degrees and the point where 90 degrees and the horizontal 0 to 180 line met. This point. I will place it here. Then, watch what happens. You make sure that the 0 to 180 degree line lies on this outline of the glass block. I'm going to rotate this protractor. All right, so that the 0 to 180 degree line will be lying on one of the lines. Look at that. To be lying on one of the lines that formed the angle we are about to measure. So watch now. The normal is lying on the 0 to 180 degree lines now. And this point where 90 and 180 degree line met, look at it. Now this is the refracted ray. Measuring from here 0 degree to this point, you will notice that the refracted ray came out somewhere here. Look at this point, which is there about 12 degrees. 12 degrees. Therefore, our refracted angle is equal to 12 degrees. 12 degrees. And we've done the major thing and the most important thing in the verification of Snell's law. Any other thing that is left based on what your examiner may need you to do, the instruction in the experiment will be given to you. Subsequently, we'll be seeing other things that are necessary as maybe your exam questions may demand. For example, this incident ray can be extended. We can produce it with a dot down to this place and then draw a perpendicular line from here to that incident ray that we produced. This distance from this point perpendicularly to the incident ray, we call it the lateral displacement. Because if you look at this, see, the incident ray was supposed to go this way, but now it was laterally displaced to this point, which is the refracted ray. Finally, the thing emerged. Another thing you should take note of is that the emergent ray and the incident ray, they are parallel. Now, let me label these rays for you now, okay? This is our emergent ray. Emergent ray. Emergent ray. This is our refracted ray. Refracted ray. Refracted ray. And of course, this is our incident ray. Incident ray. Incidence ray. Okay, it's good. Incident ray. And of course, this is our normal line. So, like I said, in subsequent videos, we're going to see other important things that are necessary for you to do. In that case, we would have an instruction to follow, exam question, all right, to see how we go about answering a full practical question. In the meantime, this is 90% of what you do in every rectangular black optics experiment. Wow, it was a wonderful one, demonstrating Snell's law using this rectangular black. And we stated from the beginning that we are going to determine the refractive index of this what? Rectangular black. Remember in the experiment, we got the incident angle to be what? 20 degrees, right?
Yes.
And then when we were done getting the refracted angle, what was the value we got?
12 degrees. 12
degrees. So now this is what we're going to do. You can also do your own using the incident angle I of 20, refracted angle of 12 to determine the refractive index of this rectangular block. So can you do that here while our viewers at home? Please be working on your own. At the end, we'll see what we got. Please, go on.
According to one of Snell's law, it states that refractive index is equals to the sine I over sine R. And your I is incident angle, while R is refractive angle. So what we do from here is I, which is equals to 20, sine 20 all over sine 12, which is refractive angle.
So let's see what that is going to give to us. All right, so sine 20 divided by sine 12. Right, so the calculator gave me 1.64.
So your answer is equals to 1.64.
So the 1.64, what does it represent?
The refractive index.
Presents the refractive index of the glass. Now, friends at home, I'd like to say this. In real practical setting, you are going to do this experiment for up to like 5 times. You know, we did it only once. In real exam situation, as you might encounter in school, the incident angle will be varied, will be changed. They will give you different value of incident angle. We started with 20. You could have 25 degrees, okay, another incident angle of 30 degrees, another incident angle of 35 degrees, another incident angle of 40 degrees, and maybe even up to 50 degrees. You would use the values of this incident angle, run the same experiment, exactly the same thing we did. You repeat it for different incident angle. Get different values of what? Refracted angle. Are you there? Yes. And then you plot a graph of sine of incident angle against sine of what? Refracted angle. And do you know what's going to happen? After plotting the graph, if you take the slope of the graph, the answer you are going to get will be equal to the refractive index of this glass that we just found out experimentally here. So, like I said, in subsequent videos, we're going to run this experiment fully, have the values with the sine of angle of incidence and sine of angle of refraction evaluated, and then we'll plot the graph and show you clearly how we obtain the refractive index of a rectangular block using the principle of Snell's law. Until then, remember we still have another important experiment to perform, which is refraction of light using, how do we call this prism?
Triangular prism.
You can look at it, triangular prism. So just watch as we do that in subsequent videos. Remember, you can subscribe to our YouTube channel and have a wonderful time as we carry you through making science, you know, for you friends at home. Thank you for watching.